Hi, good day everyone. I'm Farizmi Chong, and today I will be speaking on a brief analysis of the developments in particle physics. Before being able to provide an analysis on a topic, we first have to acquaint ourselves with the relevant developments throughout the history of physics. The answer to what is the smallest indivisible thing has perplexed many throughout time. In fact, the adjective used by the ancient Greeks to refer to that which is indivisible is atomos. Skipping way ahead in time to 1897, J.J. Thomson was able to discover electrons through his work on cathode rays. Through experimentation, Thomson was able to discover that the rays generated between two electrodes placed in a vacuum when a voltage is applied across can be deflected by an electrical field. This led him to believe that they were not a form of light but instead were negatively charged particles, which were not previously known. With this new discovery, Thomson went on to suggest the plum pudding model as the structure of atoms. He suggested that atoms were divisible and the negatively charged particles, which were later referred to as electrons, were distributed in a sea of positive charge. Thus, the electrons were the plum and the pudding the sea of positive charges. At this point, the atom is now divisible and no more the smallest indivisible thing. In 1909, however, the plum pudding model was rejected due to the discovery by Ernest Rutherford that suggested that most of the positive charges, which were later referred to as protons, as well as the mass of the atom, were concentrated in a very small volume of the atom. Rutherford assumed that this concentration was at the center of the atom. This experiment that led to this discovery is known as the famous Gold-Foil experiment. Following this development, Rutherford proposed a model of an atom that incorporated all of the newly developed ideas. Niels Bohr, in considering the contributions of Einstein and Max Planck in quantum theory, further posited that electrons can only orbit in particular circular orbits. This is famously known as the planetary orbit model of the atom. After which, in light of Louis de Broglie's proposal that subatomic particles exhibit a wave-like behavior in 1924, Erwin Schrödinger formulated the description of electron as a wave function instead of a particle. This led the way for the discovery of the Heisenberg uncertainty principle in 1927 by Werner Heisenberg. This culminated in the use of electron clouds as a model to show in a non-continuous fashion the possible positions of where an electron can be found outside of the nucleus. If one were to break up the aforementioned developments regarding their subscription to the different kind of mechanics, it would roughly look like this. As an anticipation for the later discussion, it is important to note the persistence of classical mechanics through the development. The first idea I will be relying on will be Imre Lakatos's idea of scientific research programs as opposed to Thomas Kuhn's notion of paradigms. According to this idea, each scientific research program should be construed as having a hard core which consists of fundamental assumptions, ideas and methods. This hard core sits in the middle of the protective belt that consists of assumptions, ideas and methods that are much more easily given up in the face of disconfirming developments. However, governing the internal dynamics, there are two heuristics which scientific research programs follow. The positive heuristic, which accommodates the changes to the protective belt in a progressive manner, and the negative heuristic that resists making changes to the hard core. To fill in the details, we can see that one assumption in the hard core is that Newtonian mechanics governs all particles, while in the protective belt the assumptions are that the atom is mostly filled with stuff which are thought to be either electrons or positive charges, which makes up most of the atom. This, of course, is a reference to Thomson's plum pudding model. Next, we see a change in assumptions in the protective belt, which are now that atoms have a nucleus which contains neutrons and protons, as well as electrons orbiting around the nucleus, similar to how planets orbit around the sun. No change is made to the core, however. This is in reference to the Rutherford-Bohr structure of an atom. In accordance to the latest development, there is a change in the protective belt in that electrons are probabilistically found outside the nucleus, and that they are not particles in the general sense per se, but are instead now considered as point particles. This is of course provided for by the major revision to the assumption in the hard core, as quantum mechanics now govern both particles and subatomic particles. At a glance, one may not be able to understand how drastic a change was when the hard core assumption was changed from classical mechanics to that of quantum mechanics. Let me illustrate. Consider the ever familiar pendulum. According to the classical mechanics or Newtonian mechanics, the probability of locating the pendulum at any specific location can be described by the following graph. The graph also illustrates a key feature of classical mechanics that within a specified region, the probability of locating the pendulum is always above zero. Now, consider the hypothetical simplified counterpart of a classical pendulum, the quantum pendulum. Not only the probability of locating the electron at a specified location is described by a highly unintuitive graph, there are points where the probability of locating the pendulum at a specific point is theoretically zero. Thus, we can see the cogency of Lakatos's notion of scientific research program as the preservation of Newtonian mechanics as an assumption in the hard core is independently justified by a very strong intuition of the way the world works. Following this notion of counterintuitiveness, the question rises whether we truly can make sense of what an electron cloud is when we realize that it's merely a shorthand representation of what it is in actuality, discontinuous and consisting of infinite points of where an electron might possibly be. Although this representation captures the discontinuity of possible locations of an electron, it fails tremendously in representing the infinite possibilities. Most importantly, these are not the only representations we use today. In looking at the received view of science in this field of physics, the issue of counterintuitiveness has tremendous implications on education. How are we to bring across such an abstract idea to students and teenagers? Thus, to my knowledge, many countries use the dot and cross diagram to bring across the idea of how ionic and covalent bonds work in principle. Apart from only focusing on the valence shell electrons, any notion of quantum mechanics is removed from the picture. Next, at certain levels of education systems, such as the tertiary level in Singapore, the electron cloud model is used to explain the idea of partial charges as well as the structure of covalent molecules. This includes the explanation of the polar properties of water as well as the hexagonal structure of snowflakes. The final model, the energy level model, essentially gives up hope on representing the locations of the electrons, but instead focuses on the different states an electron may have. This allows one to calculate, for example, the minimum amount of energy for an atom to lose an electron. That is all I have to say for now. In this short presentation, I've illustrated a key insight which Lakatos' notion of scientific research program has provided us, as well as the utility different models of representing an atom has provided us, all in the aim of shedding light on an evolusive electron. With that, I end my presentation and I thank you for your kind attention. Have a nice day.